Good morning, New England. Greetings from just England. Old England. Hey, steady on, steady on. We're not that old, we're gracefully middle-aging. So it's lovely to be here. Love what you've done with the place. Looks very English to me, kind of grey, brown palette, with the side of, don't mess with me, lie me, we've got plenty of space for you in the harbour where the tea chests are, right? Yeah. True story, one of my colleagues literally said that to me this morning. She's nice to you guys. So my name's Jim, and I'm Neo4j's chief scientist. Been with the company for 9 years. I'm old enough to remember when I was the only scientist at the company. So if you're wondering how I got the grand title, I just got in first. So now that I've got you enwrapped with my amazing credentials of being first in a queue, I hope to keep your attention for the next 40 minutes or so to talk about how graphs are being used in machine learning. And so I'm a fairly straight-talking person, which has my marketing team on tenterhooks. So this is the thing, now I'm on stage, they can't stop me, it's great. But there's a row of nervous-looking people at the back saying, what's he gonna say? I'm going to talk to you, I like this guy, yeah. So I'm going to give you some no bullshit definitions, because if there is an area of computer science which is prone to bullshit today, I can say this, right, because we're on the East Coast and people understand that swearing is fine and a traditional part of communication in the English language. Can't say it on the West Coast, they get all vegan on you. Hey, port cities. So I'm going to give you some no-nonsense definitions. I'm going to talk through my history of graphs. So it's a little bit kind of anecdotal, personal, this, which is, since I'm chief scientist, maybe I should be more scientific. But I've had a history with graphs now over the last decade or so as a user of graphs, and ultimately, kind of poacher turned gamekeeper, becoming part of a graph company, of building systems which had intelligent-like behaviors. And I think that's really interesting. Then we have a look through graph theory and see what we've got in that bucket of skills that we can bring to the fore to build systems that appear to be intelligent. Towards the end, we'll talk through contemporary graph machine learning and what we can do at the confluence of graphs and machine learning. And then we'll take a little peek into the future of graph AI. And that's the only time in this talk that I will say the words AI without inwardly cringing / laughing, because that is a big lump of BS. So, if like me, you're a complete bluffer at AI, this is, again, credibility with the audience that I'm meant to build, this is my guide to AI acronyms. Machine learning, ML, finding functions from historical data to guide future interactions, specifically within a given domain. So this is not cross-domain learning. AI is the property of a system that it appears intelligent to its users. I think actually achieving that goal is really, really interesting, really useful, whether or not we're using fancy machine learning frameworks to do it. Often, but not always, using machine learning techniques. Or, if you're quite high up the AI evolution chain, ML implementations that allow us to cheaply retrain models across domains. This is often conflated with plain old predictive analytics, use the past to predict the future. General purpose AI, that's machine learning with transfer learning, so that learned experiences in one domain can be applied elsewhere. You know, for example, that hitting your head on a wall hurts, so you don't try to hit your head on a desk, unless you've been in this talk for 20 minutes, in which case it becomes a slightly appealing prospect. Or indeed, human-like AI. So, ML, all the things. What we do today. Well, come on, Clicky. Thank you very much. We take tables, and we extract features from them. No, of course we don't. We could do that, but we're graph people, right? So what can we do which is better than that? we could just take our data, our tabular data, our columnar data, even our reified document data, and pump it, turn it into vectors and pump it through a regression model or a classification model or build a scorecard or what have you. And that's not a bad thing, right? I am not saying that your machine learning pipeline is bad. I say actually it's fine. You get some value from it. It helps, it helps drive value for your businesses. It brings something useful into your domain. But actually, I think we can do a lot more with data to build systems that appear intelligent before we reach for the ML pipeline. I think the ML pipeline is kind of like the icing on the top of a very tasty cake, if that cake is made from graphs, and I am definitely laboring that metaphor now. So, for the purpose of clarity, the thing on the left is a graph. The thing on the right is a chart. And what you guys haven't noticed is there's a little unit underneath each of your chairs. If you get those mixed up, I press this red button, and you get an electric shock, right? They actually chipped me at Neo4j. They've got the same thing in miniature here. If I get those mixed up, it's like, So thing on the left is a graph, thing on the right is a chart. Charts are very useful for visualizations. Graphs are very useful for storing and reasoning data. And in fact, it turns out we all know graphs. How many of you folks have come to a Neo4j event for the first time today? And keep your hand up if you're kind of still kind of graph curious rather than got graphs under your fingernails. A few of you. I'll tell you what, one slide, you're all going to be experts. Here you go, it's my hometown. It's a graph. Yeah, it's a tube graph, thank you. So, oh good, I'm not being filmed. So you are going to London. It's lovely, you'll like it. It's a lot like New England, right? But we have accents. And you're going to land down here. This is Heathrow. Don't go to Gatwick. It's like the Mos Eisley of London airports. It's a wretched hive of scum and villainy. Now, bear with me, folks. The Neo4j office is near here. This is, as you would pronounce it, Southwark, and that's how we know you're American. It's Southwark, apparently. W-A-R-K is pronounced uck. Don't at me. I didn't make up the language. So you inexperts with your large suitcases that block the tube carriages, your challenge is to figure out how to get from Heathrow to Southwark. How'd you do it? Jetpack. Okay, so there are a few executives in the room. They're already taking a black taxi. That'll cost you about $170 and inane chatter for about 3 hours in London traffic. For those of you that are like me, you'll say, well, I've landed in Heathrow, and I know the rules of a graph. I'm only allowed to traverse from one blob to another blob if there's a stick connecting them, right? So if I said to you, okay, so now you know those rules, what might be a quick way of getting from Heathrow to the Neo4j office and come and have a cup of tea with us? Oh, no, you don't drink tea, do you? You throw it in the sea. Come and have a cup of coffee with us. All right, we've got to get this off our chest, right?
Station.
Pretty good in human language. That was a technically correct answer, but he kind of undermined the pun that's coming, so thank you. You kind of follow these lines and you kind of amble your way through the network until maybe you found this and you came down here. Who thinks that you would go perhaps up the blue line, up the other blue line, round the purple line, round the yellow line, up the green line, back down the red line, down the black line, and no. Why didn't you go that way? That felt like a long path, right? So you were already able, even as non-experts, even as people who aren't called Dijkstra, no one's called Dijkstra. You kidding me? Okay, so even though you aren't yourselves Dijkstra, even you as normal human beings, you were able to intuit your way in a very Dijkstra-like way through the graph to kind of find a short path. If you're interested, and goodness only knows that my fellow executives at Neo4j need to learn this. The shortest path, by the way, is to take this blue line, change at Green Park, and then take the silver line down to Southwark. What they do is all sorts of stupid stuff that keeps them in traffic for 2 hours. So you already know graphs. What's interesting, when I was at university, as a student rather than as an academic, to learn the equivalent kind of skills in relational databases took a big, thick book. And many of you probably had that book, and it was like, first normal form, second normal form, third normal form, oh my God, normal form, right? It was complicated. The labeled property graph model can be described in one, albeit widescreen, slide. We have nodes with optional properties and optional labels. Properties are data, labels express the role of the node in the network. We have named and directed relationships, again, with optional properties. So if you're really going to do shortest path, you may have length or time to traverse a path on those relationships. Relationships never dangle. They have exactly one start node and one end node, which may be itself. So that's it. You've now learned the whole of graph, almost. Let me just bring that home to you. Now, it was mentioned earlier that many of the people in the Neo4j team are big fans of the Matrix. What you don't know is there's a competing fiefdom in Neo4j involving the BBC. I'm stealing BBC's intellectual property to teach graphs here. So who knows Doctor Who? I love you guys. Normally when I say that in the US, it's like, Doctor what? No, who? For those of you that don't know Doctor Who, I'm going to prove to you that you already know graphs brilliantly by also teaching you Doctor Who. It is, by the way, the world's longest running sci-fi show. It goes back to 1963, so, you know, shove it, Star Trek. So there's this guy, Doctor Who, he's a human, or humanoid, and the idea is that he can travel in time and space, and he's like a do-gooder. He goes around kind of sorting out problems. This is Doctor Who played by Matt Smith a few generations ago, and it turns out that the Doctor is from a planet called Gallifrey. He's not actually a human, he's a Time Lord, and he is from planet Gallifrey. So how do you read that? We say, well, Doctor from Gallifrey. So you kind of read these graphs very conveniently. In fact, when I'm doing graph modeling, I find that if I can read a sentence conveniently, it's probably a good model. So we can enrich our model. We know that the Doctor stole a space and time craft that enables him to travel around the universe in time and space. It's called a TARDIS for you new to Doctor Who fans. Time and relative dimension in space. See, if I was saying this with a New England accent, you'd all be bored now, but I know the tricks, right? You're all glued in. Oh, the English guy's saying things, listen. He has enemies, right? Because he's a do-gooder. He goes around time and space putting right things that are going wrong, and he really pisses people off. So these guys are called Daleks, and they look like pepper pots with laser guns. And I got to tell you, as a child, they terrified me. Right? But they have like screechy voices. He's also made enemies of the Cybermen. He's also made enemies of the Sontarans. And the only reason the Sontarans are in is because one of my lovely colleagues says, hey, Jim, do you see the resemblance? And it kind of stuck, right? Well, I'm owning it now, right? I'm owning it. That's fine. I'll take that. But Doctor is also quite needy. He likes to travel with friends. And because the BBC budget is low, those friends are usually human looking, right? Because you don't want to pay for makeup. In this case, he's traveling with, this is Rory and Amy, so you can see this is from you experts know this from a few seasons ago. But Amy and Rory have their own thing going on. They're in love. Rory loves Amy. Amy loves Rory. That's nice, right? They've got their own, I'm getting a bit into this now, aren't I? Yeah. They've got their own thing going on. And in fact, look, many of you are IT professionals, so this model makes a bunch of sense to you. For example, love can be unrequited. Yeah? In this case, Amy loves Rory, Rory loves Amy, but you IT professionals know that sometimes you love someone and they don't love you back because to them we're not even human, right? We know it, we've been there. We've been, oh, I feel like, you know, this is Oprah now, isn't it? Yeah. You get a book, and you get a book, yeah. Now, the thing is, while we're all talking about graphs, the lovely thing about graphs is graphs have layers. You can bring layers into your query or leave layers out of your query. And there's a real world of Doctor Who. Right, don't worry, I'm not some kind of nut job that thinks this stuff is real. I realize this is a science fiction TV show. But there are elements of this problem domain which are very real. And they come together in episodes. So we know that, for example, all these fictitious characters appear in an episode, but an episode will also be linked to the writer, the producer, the actors that were in it, the locations that were there, the bloke that's providing the bacon butties for breakfast in that particular quarry in that episode. So all of these things come together in the real world. So we can build this really rich graph of both fictional and non-fictional stuff and choose to bring layers in or out of this graph. It's very rich. And then finally, we put labels on things so that we are explicit about the roles of those nodes in this graph. So now, particularly for those of you that are new to Doctor Who, if I said, hey, how do I find out in which episodes Amy battled the Daleks, Well, you'd be able to do that very easily. You would find episodes that the Daleks appeared in, you would find episodes that Amy appeared in, and then you would meet in the middle. And in fact, in this case, you would find the episode Victory of the Daleks, badly named episode, they lost, hint, they're the bad guys. But you'd be able to do this. So even now, even those of you that are now just into Doctor Who and thinks it's absolutely amazing, you already have some expert level knowledge, right? This is great. So if you want to know, the Doctor regenerates. That's how he's kept going since 1963. The Doctor can die and reform in a new body. If you want to know who came after Matt Smith, you can simply follow the links regenerated to, so you can follow the Doctor Who history. And in fact, if you wanted to go back all the way in history through all of these historical Doctors, you can do that. Now that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Of course, I knew that number because I'm a nerd. I knew that, but I thought I'd count just for theatrics. That's 13. How many of you fancy doing a nested join 13 times on your relational database? Any takers? Okay, come on, you can do fancy indexing. No, super fancy. No? Not getting a lot of love here, folks. No, of course you won't. That's terrible. But actually in a graph, this stuff's pretty cheap to do. So it's not a problem in Neo to be able to traverse effectively through 13 joins because it's dead cheap. So in this case, I'm just looking for that star there means links at any depth between me and Doctor Who. And in fact, that's pretty cheap to do. On my laptop, which is an overpriced, new-ish MacBook Pro that I hate, can I get a hell yeah from the nerds in the room? Oh my God. I can do about 40 million traversals per second in a steady state database. So that's quite a lot of horsepower for me to be able to traverse this graph. So if I wanted to know how I'm connected to Doctor Who, and I actually am at quite a depth, this is it. This is my graph. This is my kind of bragging graph. I've got no other credentials to give you. But this is me. It's actually me on my wedding day. You can see I've deteriorated. Now I'm married, I just don't have to. You don't have to bother, right? It's great, love it. So I wrote a book. I wrote the O'Reilly Graph Databases book. And this is my mate Ian Robinson, who's also a big Doctor Who fan, and he wrote that book with me. And he's an author, and I'm an author. Ian was also a landlord. So he owned a flat, actually in Birmingham, my hometown. And he sublet that flat to an actor, at the time an aspiring actor, Chris Addison, who actually became quite relatively famous in the UK, who played a character, Ollie, in a TV series called The Thick of It, which was a political satire, or as we know it now, modern life. And in that series, The Thick of It, there was a very, very sweary character called Malcolm Tucker, who he's the Shakespeare of swearing. You guys would love it. But actually that actor, Peter Capaldi, played Tucker and played a regeneration of Doctor Who. So if I follow all of those links around, that's how I'm connected to Doctor Who. And that's super, super cheap to be able to process in a graph database. So what do we want? We want smart systems. We can take a step back, right? We don't have to gain insight or to build systems that appear intelligent. We don't have to immediately reach for our GPU-accelerated TensorFlow mega framework. We can do more with our data. Let's take a step back. Man, doesn't that seem like good days? Long time ago, it feels like a lifetime ago. Back in 2008, circa 2008, I was working for a North American telecoms company, and we were working on product recommendations. And what happened was we were going to pay about 10 million bucks to buy some software, and then we were going to customize it, and we thought somewhere between 3 and 5 years later, we would be able to deliver product recommendations to our web properties and to our call center. And that was fine. I mean, the kind of buy and then customize thing was a bit awkward. There's some arguments there, but ultimately we had a plan. And then I went to Sweden to go and speak at a conference there, which was grand. And I met this weird guy, tall, weird Swedish guy. And yeah, this story gets worse. And he's like, what are you working on? I'm like, oh, I'm doing this kind of recommendation engine where I'm trying to encourage people that have a cell phone service from us to also take some internet and take some video on demand or some cable TV or whatever. He's like, oh yeah, there's a graph in that data. I'm like, look, tall, weird Swedish guy. I know how databases work. I have a PhD. The D stands for databases. Databases have tables. Right? Square things, you put data in them, okay? Bye-bye. And that was kind of awkward, but anyway, he's like, no. Like, and I met him a couple more times, and he kept prevailing upon me that there were graphs in my data, and I kept telling him, look, man, look, this is kind of an odd cultural thing, but you need to get out of my personal space now, because you are weird with your graphs, right? Be away with you. Anyway, funny thing, that guy's my boss now, so that worked out brilliantly. But I went back to work, and I'm like, hey, wait a minute, that weird, tall, Swedish guy was right. This is the graph problem, right? Because someone's bought something, and I can see other products that depend on it, and I can also see a way to not making conflicting product recommendations by looking at a dependency graph. Ah, right. What was that thing called again? Neo4j. So I Googled Neo4j, and it is this Hellscape of Maven and Java, and oh my word, it was horrible. I'm not even kidding you, it was the biggest, horriblest thing. Anyway, about 10 hours later, I've gone through the Maven Hellscape of Java badness, and I've written a query. So you guys write sci-fi, I had to write stuff like this, which apparently to Swedes, that's nice, right? Yeah, try taking that to the boss. So I'd written something like this, and I ran a query. And then having told the system that I already had broadband service at home, it could look at the dependency graph, say, well, if he's got broadband, he must have a modem. If he's got a modem, that means we could sell him, he's got a modem, does he have a telephone? Yes, if he's got a telephone, we can sell him voicemail. But if he's got a modem, we can also sell him the next higher tier of broadband. And because it was just a dependency graph, there was never a chance they would try to sell me something I already owned, and there was never a chance they'd try to sell me something that was conflicting. Compare that to Amazon. Check these bad boys out. Bought a pair of shoes off Amazon because I'm a middle-aged white guy. That's what we do. What does Amazon do now? Recommends me shoes like I'm an octopus. Right? Statistically, I have a slightly higher than average number of legs, but as a biped and a middle-aged white guy, I buy shoes about once every 5 years. Now, Amazon's recommendation engine hasn't figured that out yet. Our recommendation engine did. This, though, blew me away because in one long afternoon, we'd solved the recommendation engine problem. Buy me a beer later if you want to know how delivering that incredible business result got me fired. Politics. I thought I'd invented Skynet because we'd built a system, albeit very skeletal system, that appeared to me to be intelligent as the user, and I'm genuinely not even kidding. When that result came back, for a few seconds I was genuinely flabbergasted because the system appeared intelligent. Then there was kind of a rational part of my brain that reasserted itself. It said, Jimmy, it's a patronizing thing, the rational part of my brain, right? Jimmy. That wasn't AI, that was a graph search. That was that thing that you forgot from Algorithms 101. Oh, yes, how it was. Thanks, patronizing part of my brain. And then suddenly it's like, wow, this is nice. With data structures and algorithms, we could build systems that appeared to be intelligent. So it wasn't AI, but it was extremely effective. It was strong, it was unexpectedly powerful. In one long afternoon, we solved a problem that we thought would take us about 3 years to get solved with traditional tech. My thoughts were, well, we wrap a Rails front end around this, deploy to the call center, deploy to the website, collect accolades. So then over time, the stuff matures. Neo4j grows away from its Java Maven Hellscape background, becomes a server. That was my first contribution. I built the Neo4j server, and then we put Cypher around it. It's amazing and humane to implement. I was back in the UK some years later, and we started looking at purchasing behavior for a large supermarket. And we were enamored of this folklore from the US that on Friday nights, if they put diapers at beer at the end of the diapers aisle, they sell more of both. And we were interested, that was a hook for us, it was quite entertaining. So what we did was we took a bunch of transactional data and a bunch of taxonomical data, so categories and baskets, and we stuck them into a graph. And it looked a little bit like this. We created a bunch of purchasing data. And what we observed was, we had this kind of, our test case was this young father's pattern. That is, do I have someone who has a certain age and likely gender, who's bought a game console, who's bought nappies, diapers, or who's bought beer? And we thought that that matched very well this kind of Friday night beer and diapers pattern. And so we've got a pattern to search for. Now, if we'd ran this through like a machine learning framework, we know that's what it decides. I can't believe I snuck that past marketing. Actually, it's on my screen here as well, so I can't avoid it. There's a guy taking a photograph of it. Sir, stop! This is the worst. The hilarious thing of this is I know this was recommended to me by a deep or convoluted neural network, so Graphs even gave me this horrific picture that you see in front of you. But actually, apart from the giggles, this is a huge business opportunity, because if you spot someone that partially matches this pattern, you have an opportunity to upsell them. So if you spot someone that's bought beer and nappies, but hasn't bought a game console, you can sell them a game console, or you can nudge them to do a game console. And what we wanted to do is do all of this in real time. In the old days, the way that nudging people worked in UK stores was you'd swipe your loyalty card, a couple of weeks later, some vouchers come in the mail, you think that's spam from the supermarket, you stick it in the recycling. Actually, what you want to do is, it turns out that we're working with a bunch of psychologists, and the psychologists were telling us that humans, on the whole, are not psychopaths. I know this looks odd, doesn't it? Now it's like, why is he messing with his jacket? Humans are not psychopaths, and so what you really want to do, the psychologist told us, is you want some human contact. There you go.
Thank you, Kat.
You're welcome. Thank you for not being a psychopath. That will fail me one day. Gentleman at the front, I gave him a business card. It's awkward, right? Because he's seen me messing with my jacket. He knows something's going on. And yet when I gave him the business card, he immediately read it. That's now impacted him. What we want to do is print out the vouchers and stick them in your hands, because unless you're a psychopath, you'll take them and you'll look at them. And that encourages you to change your behavior 1,000-fold more than getting some vouchers of similar quality in the post. So what we want to do is be able to flog you stuff that seems intelligent in the clickstream. What we don't want to do is antagonize you. So one of the things that the psychologists called a contraindication, or we as developers called taking the piss, was when you're at the checkout. I'm a northerner, we can say it. At the checkout, beep, bananas, beep, I don't know, what's doing, roast beef, English, yeah, there we go. Beep, PlayStation 4, and then checkout. Vouchers get printed, 20% off Xbox One. Right? I'm faking it, but I still actually feel quite cross about that. Like, I've given this talk half a dozen times now, and it still makes me angry that they printed out a voucher for an Xbox One when they can see I've just bought a PlayStation 4. Any human can see that's wrong. So what you need is to bring this right into the clickstream. In fact, you can do that. You can take that graph, you can turn it into ASCII art, you can straighten it out, you can surround it with a bunch of technical gobbledygook from Neo4j language, run this, bind it to parts of the graph, and get results from it quickly. If you're wondering, in my world, Rory Williams, a Doctor Who character, comes out as an ideal candidate to sell to. So you can either do this at global population level, run it as an analytical job, or Neo4j is quick enough at 40 million traversals a second to do it in the clickstream as people are going through the point of sale terminal. This was amazing. It's the kind of thing that Facebook does with graph search. So you've used this stuff. Which are the sushi restaurants in New York City that my friends like? And it's this kind of graph. It's me, I'm a friend of Andreas and Michael. Michael likes ice sushi. Andreas likes Sushi-Zam. They're both in New York and they both serve the sushi cuisine. Trivial, absolutely trivial query. And even though that might be a huge data set, this thing comes back very quickly, because in graph world, in Neo4j world, the latency of your query is proportional to how much of the graph you want to traverse. It is not proportional to how much data you've stored. So you are not paying, for example, the set-based penalty that we're all afraid of from relational databases. So, graph theory. And I realize now that I don't have a clock on this thing. Oh my word, have I really been blathering for 40 minutes? Michael's going to be speaking really quickly in about 20 minutes' time. Graph theory, rich bunch of cool stuff going on in graph theory. These two books, once you've read O'Reilly's Graph Databases, which is like the premium book, obviously, on the subject, These two books, plus the Graph Algorithms book by Amy and Mark at Neo4j, are brilliant. These are a bit more academic-y, so you can look a bit more highbrow with these. They're just amazing books. But graph theory is a rich toolkit of things that you can do to analyze your data and give you intelligent-looking answers from it. First part of our book of tricks in graph theory is this notion of local properties. And graphs are a bit weird, right? In graphs, small things, localized things, can often have dramatic global effects. So the first skill that we learn in graphs is this notion of triadic closure. It's a bit of a kind of highbrow way to say make a triangle. But that's what graphs have, particularly graphs involving humans. So you can see here, I've got a small social graph. Bonus points if you know the cartoon series that I stole the names from. You can see that Kyle is friends with Stan, and Kyle is friends with Kenny. And you've seen this. Okay, some of you have seen this. Some of you IT people with friends. I know it's a bit of a push, but come on, it shames me as well, okay? Yeah, I'm South Park, thank you. And so you can see, like, in your lives, you've seen this kind of thing. You've got two friends. Somehow, transitively through you, you're kind of sure those friends are kind of compatible with each other. So over time, those two friends themselves become friends because there's kind of transitive trust between them, right? That's kind of cool. There's also this notion of structural balance. So in this case, we've got Cartman, who's a friend of Craig, and Cartman, who's an enemy of Tweak. So it's a kind of interesting thing here that you could form a triangle like this, where Cartman is a friend of Craig, Craig is a friend of Tweak, and Cartman is an enemy of Tweak. But this is awkward, right? Because Cartman's like, hey, Craig, let's gang up on Tweak and prank him. And Craig's like, no, Tweak's my mate, I'm not going to do that. So that's kind of an awkward thing. Yeah, and you don't really want those kind of awkward friendships around you, right? And as an awkward person, I feel this acutely. So what you really want is this kind of thing. I mean, you don't, because it's horrible, right? This is terrible. But now, at least this feels normal. Now, Cartman and Craig can both hate Tweak, right? I'm not saying that's like moral, but it's stable, right? So those little things. So that's kind of sad. But what you could do, a stable structure, would be this. So you could have three friends as a stable structure. And that's much nicer. So this notion of structural balance is a key predictive technique, and it's domain agnostic. And I'll prove it to you. This is the starting point for one of the world's worst periods of history. This is actually a network of the great houses of Europe. You are, by the way, conspicuous by your absence. Thanks, that's great. What, are you still holding a grudge about 1776? Come on. So this is a point in history that historians call the Three Emperors League. And you can see that you've got UK, Austria, Germany, Italy, France, Russia. In this graph, the red arrows indicate enemies, and the black arrows indicate friendships. Hence the Three Emperors League here. Austria, Germany, and Russia are in league. Or as I think of all of the Bond bad guys. Italy wants in on this. So it forms a structurally balanced closure with Austria and Germany, right? That's fine, the graph likes that, they're friends. That's good. And then the Germans and the Russians kind of fall out. And then there's a kind of three-way enemyship there. And that doesn't feel very stable. The graph doesn't like that. The graph rejects it. It wants to make these things stable. So what happens is that France and Russia naturally gang up so that if necessary, they can take on Germany. Right? That's a stable thing. I'm not saying it's moral, but it's stable. Two countries gang up on one is a stable configuration, a low energy state in the graph. Then something weird happens. Est-ce qu'il y a défoncé dans la salle? Brilliant. So this is the weirdest thing in history. This is when the French and the Brits are friends. You guys know the French, right? They liberated you from us. Yeah. So we're holding a grudge at this point, but then we become friends. And it's called my schoolboy French isn't very good. It's called the Entente Cordiale, which if you translate it into English means we surrender. Right, and then that's weird, because like now Russia, the UK and France are in this kind of unstable, awkward demographic. So what happens is that the Russians become friends with the Brits. We iterate over the graph, we make more triadic closures, and eventually the graph kind of naturally falls into this low energy state, where you've got only balanced closures here, which is brilliant for graph theory, right? Because this is now the starting point for World War I. It sucks to be a human that we've allowed it to get this far, right? You know, can't we just pick up the phone and talk? It has recently been invented after all, but now this is the starting point for World War I. So you can actually predict, particularly in social networks, the behavior of things in the future. I stole this from Easley and Kleinberg. It's a bit sad, but that's not my kid, so I don't care. If you want to know more, pick up the Easily Inclined Bird book. It's amazing. There's one other property I think which is very interesting, like triadic closures can also have strength. And these weak relationships play a profound part in understanding graphs because they separate neighborhoods. So in this case, Stan and Cartman are kind of half friends. They don't really like each other. So these weak relationships form bridges, and you can see that here. Even though that weak relationship between Stan and Wendy there, it's called a weak relationship, actually you can see it is the single point of contact between the playground boys and the playground girls. If anything wants to go between those communities, it goes via Stan and Wendy. If this was an org chart, this would immediately make sense to you. You know where those weak links are in your org chart, where the information flows. So we can use these local bridges to start to pick apart graphs and see how they naturally decompose. This is a graph of Zacharys Karate Club. It's from the 1978 US Journal of Anthropology. Yeah, the cold winter nights do fly by in my house. Thanks for asking. What's happened here is that the Karate Club has grown from the original student instructor, marked Node 1, to as club's grown, they've brought on a professional instructor, marked Node 34. But because people suck, there's politics here. The club starts to kind of have friction. Some people like the professional instructor, some people prefer the old student instructor. And so what we want to do is say, can graph theory predict how these social interactions will add up? Now, graph partitioning is an NP-hard problem. It's algorithmically complex, but it can be done. And if we predict using graph theory how the club will split, it looks like this. And you can kind of see with your human eyes that seems about right, the kind of pink clump and the right clump. You can see where the pink nodes and the white nodes are more embedded. And that is predicted by graph theory. Now, because this happened in 1978, we actually do know what happened. Who thinks that this is correct? Yeah, I'm with you, man. I'm bold enough to say that. It's just watch node number 9. Ah, so close, so close. So actually, node number 9, student 9, should have gone with the professional instructor, as predicted by graph theory. What graph theory doesn't know is that student number 9 was about to take their black belt exam under the original instructor. And even though the graph says you're more embedded in this neighborhood, student number 9 stayed with the original club. Now, you can do this in Neo4j. You can do this stuff very conveniently in Neo4j. Neo4j comes out of the box with a bunch of useful graph algorithms where you can just declare, oi, database, process this for me, do label propagation, find weakly connected components, and so on. And that's trivial to do. We roll out with a bunch of algorithms that are production ready, and there are a bunch of algorithms that kind of lab standard that you can experiment with. And it's fast. Now, normally when you want to run these kind of huge analyses, you phone your nearest carbon-emitting thermal power station and say, crank up the output, lads, I'm bringing Hadoop into play. Actually, because Neo4j is a native graph database, this stuff is actually very quick. This is a PageRank. This is a friend of mine, colleague of mine, Michael Hunger, said, you might like this. I've got what is now a kind of pathetic desktop computer, and I ran PageRank on a large payments graph, 300 million nodes, 18 billion relationships graph. 20 iterations of PageRank took about 2 hours on what is now, I think you'll agree, kind of less than commodity hardware. If you're going to do the same thing on Hadoop, I don't know, maybe you've got lots of nodes, maybe you can do it in a week. Good luck. But the point is having that locality and having the native processing engine that understands graphs, not flat files, is super good. Michael, I'm sorry, I'm taking up your space. I'm talking as quickly as I can, and the people are desperate for you to get here. This is how AI was presented to me, right, as a kid. There's a bunch of millennials here who are like, who? This is the guy that liberated Germany from communism, if you were wondering. In the car, I like to think, right? AI was presented to me as this as a kid. AI, the natural home for AI would be in the dashboard of a vehicle, right? I'm not sure how I feel about that anymore. Now I know what computer programmers actually do for a living. But look, graphs and AI are natural bedfellows. There was a wonderful paper from KDD 2015 by Thackeray et al. And what they did was they analyzed a social network looking for interactions that was spam. And they only analyzed the structure of the graph. They did not look inside the messages for like Viagra or Nigerian prince offers you free money kind of thing. They only looked at the structure of the graph. And what they found was, by extracting features from the graph, features that are native to graphs, a page rank, a degree, a color or a label, they were able to classify 70% of those spammers with 90% accuracy before they even did any further I think I just got told I've got 5 more hours. This is great. Thank you, Blake. Before they even did anything, which is really useful, right? Because what would you traditionally do to figure out spam? You'd look at the messages, right, and try and classify them. What we're saying here is that graphs, the structure of the graph itself, leaks a bunch of useful information which you can take advantage of to build intelligent-seeming systems. Now, most of what happens in graph ML is still about extracting stuff from a graph, whether it's a graph feature or extracting property data from the graphs. So you extract data from your graph, turn it into vectors, and pump it through your ML pipeline. This is fine, right? I think this is actually quite nice. You can mix structural data with property data in order to get even better predictions out of your model. But we don't always have to vectorize graphs. So for example, knowledge graphs, this kind of, I think of knowledge graphs as kind of an evolution of the data lake. You pour the sum of your knowledge into the graph and then exploit that knowledge in domain-specific ways. We've seen these be very successful at scale. For example, the eBay shopping assistant that runs on your Google appliance. You can talk to it and it will guide you through a shopping experience with eBay. An incredibly large dynamic catalog, incredibly large user base, and it can figure out that when I talk to it and I talk about bags, because of my context, it knows I mean laptop bags, and I do have a fetish for laptop bags, that is true. It knows if my wife spoke to it, she's probably thinking about, because she's high maintenance, she's thinking about upmarket handbags, like from designer brands and so on. And that context is easily distilled from our context in the knowledge graph. We're then able to go a step further and say, well, we've got graph convolutional neural nets. This comes from ICLR 2017, and there's a really good presentation by Andrew Doherty about this. But the idea is here that we can take k-partite graphs and begin to turn them into non-trivial recommender systems. Bipartite graphs, user likes movie, trivial. K-partite graphs, user likes genre of movie, with actor directed by blah, 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 much more sophisticated. So what we do here is that we start at one corner of this problem, take a graph of users that liked a particular genre or users like a particular movie, feed it into a neural net. Take a graph of users who once rated one of those movies, for example, feed it into a neural net, and then recursively train those neural nets up until we've got the full k-partite system in there, and then we've got a recommendation engine. Far more sophisticated, as I say, than A likes B. In fact, if you think this is kind of a circuit diagram is computer science, it's not. If you've ever used YouTube, this technique is radicalizing a whole generation of young people. As we stand here speaking, right? Actually, it's not for my kid, it's like watching Lego videos, but for kind of like, lonely young white men in their basements, it's radicalizing a whole generation of young people. This algorithm apparently learns our proclivities and then amplifies them back to us. So if you're running a business which benefits from that, this algorithm is incredible, and it's a graph. But as we get to the top of the structure, the kind of, and this is the first time I will say AI and genuinely mean it. There was a position paper from, I think, probably the strongest consortium of AI practitioners in the business, which is Google, MIT, and Edinburgh University in the UK, but maybe not for much longer, you know what I'm saying? And the position of these researchers is that if we're going to build transfer learning, human-like AI, it's going to involve graphs. The reason is that we need some kind of structure, hierarchies, to be able to hang our learning from and to be able to cross-learn between it. Again, the example of bang your head on a wall, you don't need to bang it on a table to learn that it hurts. Now, this is early stages, but if some of the frankly, the colossi of artificial intelligence are thinking that graphs are going to be fundamental to AI, I am not sufficiently qualified to contradict them. Their goal is to produce via graph tech, perhaps not graph database, but via graph tech, transfer learning so that we can generalize beyond direct experience, just like we can as humans, which is kind of incredible. Now look, all of this stuff might seem hard at first. I'll credit Mark Needham for this. I think all of us, even those of us at Neo4j, we initially you have to unlearn so much to become comfortable with graphs. Where are my normal forms? how do I index this, all this kind of technical stuff going on. But once you're over that hump and you're in the I love graphs part of the curve, you are never going back. I went back once. When I was writing the O'Reilly Graph Databases book, and my kind colleague said that I had to write the relational databases comparison section. And he will attest that I was a grumpy, sweary, unpleasant human for about 6 weeks when I was doing that. I am never going back up that curve. So look, lots of stuff going on in graph world. Lots of opportunities for us to connect dots and build brilliant, intelligent systems. I'll leave you with one plea, that this is not the graph we should build. Fun as it might be, there's a lot of stuff going on. If you can reason about your data as a graph, you can already do so much to build towards building intelligent seeming systems. Taking that graph data and then extracting connected features out of it for ML processing is a way of adding a layer of icing to that cake. And composing those two practices together, I think, is eminently sensible. So look, folks, thanks for listening. I'm going to hand over to Michael now. If you've got questions, I'm going to be around all day. Please grab me, and I'll opine some more. So have a lovely day, and thanks for listening.